Uploaded a new version yesterday. Oh, okay. And then I figured out they actually needs to download it here. To have a new version. Download. Do you have a new version, or it's just the one you said last week?
I used the extended deadline.
Oh, yeah. Yeah, it works. My new ending. So you just come this trip or to go?
I'm also mobile working and have a research visit here at Space Telescope with the Star and Planet Formation Group. So yeah, Will Fisher and Nicole are on them. Yeah. The collaboration.
I see. So you'll be here for a while.
Yeah. And you? You here?
No, I just come here for the conference. Yeah.
Very basic.
Nevada. Yeah. Another conference. After this, I'm like another like code.
Yeah.
More like code. It's very spring semester. Spring break.
Yeah.
So I could travel really easily.
That's good.
How long will be here?
Until May.
Until May.
So a good month or two visit. Yeah.
That's good.
Yeah, it'll be nice to see yeah, I will visit Phil Armitage and the Flatiron with Carlo in April.
Right.
Visit Goddard Space Flight Center as well.
Oh, so you will go to CCA in April, at the beginning of April?
Yeah.
Okay. Yeah, I'll be there. I'll give a colloquium at CCA.
Oh, okay.
And if you said they will have a short meeting.
Yeah, I think people have figured out the pointer already. They just need to like press for a long time, and then the cursor shows up so people online can see it too. And the remote for the clock is here. So yeah, so M3 is the countdown mode, and then you just time, which is 25. Oh yeah, that's a good point. Yeah, I think it was a mistake and I corrected it, didn't I? That's fine. So F3 and then enter the time is 25. And then press play. And then if you want to reset, just again. Oh no, I like for the horn. Yeah, and people have been pretty good about staying on time. So yeah, you just push it up and down. And then the talks, I mean, one's already loaded. Okay, yeah, that's all good. Yeah. Thank you. So, the talks, I can open them up already. So yeah, the talks are ordered by last name, so should be pretty easy. The first one's open, but then and it scrolls the opposite way of how I scroll. I don't know how you scroll. Yeah, so the Gomez de Castro, and then.
And is this like the most up to date? Because I know some people have been updating.
Yeah, that was re-downloaded today.
Okay,
And
great.
Thomas
that's
re-downloaded
right.
everything.
That's
Yeah.
right.
So we should be good with that.
All right. Okay, great.
Yep. All right. Thank you for sharing.
Thanks for the orientation.
The 3 minutes. Okay, 3 minutes. It's fine. I probably will not use all my time. Oh yeah. Oh yeah. Okay, cool.
Okay, welcome back, everyone. We're going to go ahead and get started with the next session. My name is Catherine Espayat, and I'll be chairing this session. Our first speaker is Jiawan Zhu, who will be telling us about global 3D magnetospheric accretion simulations.
Okay. Yeah, thanks. Thank the conference organizer for the invitation. And disclaimer, this is a theory talk, and I won't have any spectrum to show in the talk. So I know this is disappointing, but please bear with me. Hopefully you still find it interesting in its own right. As we heard, the Ulysses program studying the low mass cool star focuses on the magnetospheric accretion. So we are basically probing the magnetospheric accretion physics. And magnetospheric accretion is a very general and it's very fundamental process. You only need magnetized objects and accretion disk, and you put them together, they undergo magnetospheric accretion. This was first proposed and studied in neutron stars, low mass X-ray binaries. And you have a low mass donor star, have Roche lobe overflow to form a disk around neutron star. And this magnetospheric accretion is very important for the spin evolution of the neutron star, quasi-periodic oscillation of the neutron star inner disks. And also recently is proposed to explain the recent discovered ultraluminous X-ray sources. So for young stars, we heard that these magnetospheric accretion is very important to produce these accretion signatures, which are probed by Ulysses program. And this magnetospheric accretion is also important for the disk variability and also planet formation. And the magnetospheric accretion could even happen around planets. So if the central object becomes like a planet, and the magnetized planet, and you have circumplanetary disks, they may be produced H-alpha emission lines, and you could detect, through this, you could detect planets. For example, these are the two H-alpha point sources within the cavity of the PDA-70. And these H-alpha sources could be produced by accreting circumplanetary disks, and the circumplanetary disk is undergoing magnetospheric accretion, have H-alpha lines. Okay. So first, I want to talk a little bit about the observations from different communities, like neutron stars, where all this starts. So with low mass X-ray binaries, because it's X-ray pulsation, so you could get the spin measurement very, very accurately. So that's one thing very special about the neutron star. So for this X-ray, low mass X-ray binary, you could see the spin is spinning up for many years, and suddenly it's spinning down. After another 18 years, it spins up again. And if you track the X-ray flux, there seems to not have any like sudden jump during the spin reversal or the torque reversal. With a modern instrument, you could actually track the spin evolution very, very accurately. You could even derive the slope of the spin evolution. So you could clearly see that during some period it's spinning down, and suddenly it's spinning up. Right? And you could correlate this with X-ray flux, the short period X-ray flux. Then they all correlate very, very well. Okay? When it's spinning down, the flux is low. When it's spinning up, flux is high. So this is actually consistent with magnetospheric accretion picture. On the other hand, people don't know what happened here, why you could suddenly have a spin up and suddenly have spinning down. Over decades, this is still unsolved mystery in the low mass X-ray binary. For young stars, we have seen this picture many, many times. But if we put physical scales here, this magnetotruncation radii is roughly around 0.05 AU. And beyond that, the disks is still threaded by the stellar magnetic field. So the disk still could be turbulent due to magnetic rotation instability until you reach to around 0.1 to 0.5 AU, where dust do not sublimate. You have sodium in the dust, and then they will suppress MRI. It's a dead zone. If we look at exoplanet demographics and put these two critical radius in the picture, they're somewhere here. So you can see a lot of exoplanets were discovered in a region could be significantly affected by magnetospheric accretion if they were formed in disks. Okay. So magnetospheric accretion is very important for planet formation, although currently we do not see how they formed in these disks. The theory on the magnetospheric accretion was proposed more than half a century ago. And the basic idea is that you have accretion disks, and you suppress the magnetic field. And whenever the magnetic pressure balances the ram pressure of the accretion, then material starts to climb the magnetic field and accretes to the star from the polar direction. Okay, so this is a generally accepted picture, but the detail of this picture is far from settled. For example, Frank Xu suggested that for conducting fluid, magnetic field could not pass through a conducting fluid. So all of the magnetic fields needs to pinch up at this so-called X point. So all the magnetic fields passing through this point, and then beyond this X point, you have this fan-shaped outflow. And this is very popular in meteorized solar system community. They think this outflow will transport material further away, reprocess dust to further away in the disks. So another modification is that if you consider the magnetic field connecting the disk and the star, and the disk and star are rotating at different rate, so the magnetic field has to be winded up. So in order to sustain a steady equation in this model, you have to have very high resistivity in the disks. Otherwise, as long as the field gets winded up once, like here, winded up once, then you'll have magnetic reconnection. So magnetic reconnection will produce these magnetic bubbles in the disk and produce outflows. So you'll be unsteady accretion. So this is some of the analytical theories proposed before. And there were simulations to carry it out before just to verify these pictures. However, most of the earlier simulations use viscosity in the disk. So this disk is alpha disks. And it's not a first principle self-consistent MHD simulation. And for MHD simulations like showing here, due to the computation cost, it runs for a very short time scale. The disk has not fully reached steady state. How to study accretion and outflow. And so it mostly focuses on the magnetosphere. So with the new numerical code and the more computation power, we decide to revisit this problem. We have many questions we want to answer. For example, for stars, we want to know where does accretion occur, really at the pole or somewhere still at the midplane. And how steady is the accretion? This can be compared with observation. And how is the central star can be spin up or spin down? So these are about the stars. And for the magnetosphere, what is this magnetic truncation radii? Can we really calculate it? And does really there is an X point in the picture? And where are the outflow generated? Can we generate jets in this simulation? So these are all the questions we want to answer. To make the things more complicated, we want to answer how all of these depends on the stellar spin and the disk and the magnetic field geometry of the star. So in the rest of my talk, I'll talk about this part first, just using an example that the central star is not spinning. It's a non-spinning star to illustrate this point. Then I'll talk about how all the things could change if you allow the star to rotate. So this is a simulation we did. It's Athena++ simulation. We use a Cartesian grid with a 7-level mesh refinement. And it has a long rotating star at the center. It has a dipole field, the simplest geometry you could come up with. Although we are not focusing on the star, but the star is actually resolved by 1 million grid cells. It's very high resolution. And this is actually moving. So you could see that the first thing you notice, the disk is very, very turbulent. It's not a steady accretion. It's very turbulent accretion. And also, the disk is very thick. Unlike the traditional picture, the disk is very thin. That is because in MHD simulations, this part of a disk is magnet supported. It's magnet elevated disks. And the third thing you notice that the magnetic truncation radii is not a clean cut. You will have these filaments penetrating through the magnetic spherical truncation radii, and then they will climb the magnetic field somewhere, and eventually accrete onto the central star. So it's like this multiple shell structure. You could see there's a multiple shell structure here. So if we make a vertical cut, so we can see that the density does has a drop at the midplane, but the density drop at the surface is not significant. So it's a continuous accretion from the disk to the star at the surface. So this suggests that it has a very thick magnetized disk with surface accretion. If we look at the midplane, you see these fingers penetrating through the disks. And this is known before. This is basically, if you just focus on the vertical direction here, so the upper part is high density, the lower part is low density supported by magnetic pressure. So this is really Taylor unstable. That's why you have these fingers. People have seen this before. So this is the lab experiment I did last week to show magnetic spherical accretion. Just put milk in the water. Milk is a little bit heavier than water, so they sink through these fingers. So it's exactly the same physics happening here. So, so because there are fingers penning through the magnetosphere, you could actually calculate where the hot spots are on the stellar surface. So you notice that most of the accretion is still happening at the pole, around 30 degrees. But there are these penetrating fingers that could accrete around the equator or close to equator. And then where this accretion spot is actually also depends on the star's size. If the star is a little bit bigger, then that will be easier for these fingers to penetrate through. Then you will have more accretion around the midplane. If the star is smaller, then most of the material will still climb the magnetic field. They will accrete more towards the pole. So, so there's most of the accretion is still around 30 degrees from the pole, but some are equator due to filament. And when we do the simulation, it's very hard to quantify the hotspot because it's a continuous distribution. Right? How we define it's a hotspot or not. So we come up with a criterion, say if 80% of the flux coming from some region, we say it's a hotspot. So it's very encouraging to see from Kelly's talk that now they could quantify how this hotspot distribution, how it distributes. So from here, we say hotspot covering factor is more than 20%. And we could actually also measure the speed of the inflow material. They are very close to the free fall speed. So it's also consistent with observations. Okay. So we could also measure the accretion rate around the sphere, across the sphere around the star, and the outflow rate further away from the star. So overall, the accretion is relatively steady. The standard deviation for the accretion rate is like 23%, pretty steady accretion. But the outflow is highly non-steady. So the outflow rate for non-rotator is very small. It's less than 1% of accretion rate, and is highly variable, like here. Yeah. So why the outflow is highly variable? So if we look at the movies at the midplane, so you notice that sometimes at the magnetic truncation radii edge, it produces these large-scale magnetic bubbles. So this is an extreme version of the Rayleigh-Taylor instability. And this bubble could rotate at sub-Capillarian speed and exist for several orbits and disappear. But they come and go, produces this non-steady outflow. And these magnetic bubbles is very similar to the accretion disk around supermassive black hole. So this is a disk around supermassive black hole entering this called MAD state, magnetic resonance disk state. So you can see these bubbles here. And this MAD state, people think is what they observed with the Event Horizon Telescope around M87. So it seems the disks at different scales, they could share the same physics. So these magnetic bubbles, when they orbit around the star, they will also produce small modulations of m dot. So these are the period diagrams for total mass accretion rate. You have a period here around 5, orbital period at truncation radii. And if we calculate the period diagram for mass accretion rate at 1 azimuthal angle, basically trace the hot spot, then this hot spot also has like around 3 to 8 orbital period. So remember, in this case, the star is not rotating. So you do not have any rotation period of the star. So all of this peak is due to this magnetic bubble moving around the central star. Yeah. So to summarize this part, for non-rotators, we have this new picture from the 3D simulation. You have this Rayleigh-Taylor instability or interchanging instability at the inner edge. You have both polar accretion and midplane accretion, and with a small covering factor. Accretion is relatively steady, but outflow is highly unsteady. You have these large-scale magnetic bubbles have some periodic perturbations in the disks. So now how this applies to realistic disk. We know realistic disks, realistic young stars also rotate. So this is the next thing we did is we add rotation of the star to see how the rotation affects this whole picture. So when you add rotation in this picture, you introduce another radius. That radius is the co-rotation radius. So that is where your disk's capillary frequency equals your spin frequency. So if the co-rotation radius is larger than the truncation radius, this is called slow rotators. Then the accretion from the disk to the star will spin up the star. In the extreme case, where for non-rotators, in the first part of the talk, you could think about that this co-rotation radius is at infinity, RC is infinity. And then the accretion will spin up the star. And when the star gets spins up, the RC will decreases and eventually reaches the equilibrium spin state when the truncation radii and the co-rotation radii are equal. If due to some reason, if your co-rotation radii could be inside your truncation radii, then the accretion will actually slow down the star, and this is called the propeller regime. So we have carried out different simulations with different stellar spin rate. On the left is a slow rotator. On the right is a fast rotator. Okay, so this is also a movie. So for the slow rotator, it's very similar to what we have seen before. You have these penetrating filaments, and at the truncation radii, you have these magnetic bubbles generate and disappear all the time. But if the star spin rates start to increase, you start to suppress these magnetic bubbles, and you also start to suppress these filaments. Okay. So for these cases, you almost do not have filaments penetrating through the midplane at all. That's because rotation will suppress the Rayleigh-Taylor instability, interchange instability. So it becomes more axisymmetric. But you also have this very non-steady outflow. You can see here. Okay. So overall, spin, the most dramatic effect is suppress this interchange instability. And it will make the accretion more towards the pole. So this maybe have observational signatures, because if you look at where the hotspots are in all this simulation, you find that for slow rotators, you have a lot of hotspots close to the equator. But for fast rotators, you have hotspots more close to the pole. It's more like a ring structure than these cases. Okay. And if we track how these hotspots rotate around the star, we could also calculate the periodogram. Then you find that there are many, many peaks. Some of the peaks are related with the spin of the star. They are at the spin frequency. Okay, here, the dotted line is the spin frequency. But there are also a lot of peaks which is not related with the stellar spin at all. And these are peaks due to these magnetic bubbles in the disks. And roughly around like here, they have peaks which do not correspond to any spin in the system. So the hotspots, not all hotspots orbit at the spin rate. There are some these quasi-periodic signals which could be related with the QPOs in low mass X-ray binary. But it could also be maybe observable. There were several times the orbital period at truncation radii. So you have very, very specific period. Okay. So we could also track the accretion rate to see how the accretion rate affected by the stellar rotation. So you notice that with faster spin, the accretion rate is actually gets weaker and is more variable. And the outflow rate, this outflow rate gets stronger. These are different scales and more variable too. And if you divide these two, outflow to the inflow rate, you could calculate that the ratio, also sensitivity depends on the stellar spin. It increases from less than 1% from very slow rotators to these fast rotators to 40%. And we could also calculate how the star will be spin up by the accretion. For slow rotators, as expected, they will be spinning up. And for the fast rotators, it will spin down. And when this truncation radii equals RC, as expected, they'll have zero spin, zero torque. So it's the equilibrium state. So if you focus on the equilibrium state, where most of the stars should be, then the outflow rate to the accretion rate is around 10%. So this is to the ball part of the observation. The outflow to the accretion is at 10%. So this is how the equilibrium state look like. This is a short period in the simulation, so you could capture that. And you could see that the accretion, there are still a lot of accretion from the pole. And then you also have these dark colors showing the midplane filaments accrete to the star. Yeah, so there could be these hot spots. Yeah. So this is an equilibrium spin state around young stars. So if you check all the properties during this equilibrium state, you see both polar accretion and mid-plane accretion hotspot, and it also produces jet. So in this case, you have outflows at around 500 km per second, very fast outflow. So this is the jet produced by this magnetospheric accretion. And it also has specific prediction on the magnetic field geometry in the jet. Okay. So overall, to summarize this part, for the slow rotators, we have polar equatorial accretion. Fast rotators, you only have polar accretion. This is due to you don't have filaments for fast rotators. And for fast rotators, it's highly variable accretion outflow. The ratio between outflow and accretion is also higher for fast rotators. Okay. So in future, the first thing we plan to do is we consider that the magnetic dipole and the rotation axis are not aligned. I think for most of the young stars, it's not guaranteed the magnetic dipole and the rotation dipoles are aligned. So that's the easiest thing we will do next. Then we will do radiation MHD, and this is something we're still trying to explore to see whether it's feasible, so we could get the temperature right in the simulation. If we have right temperature, then we could produce line profile, hopefully, eventually, compared with observation. So towards the end, I also want to highlight a work you have seen yesterday by Arturo, my students, who put a planet, hot Jupiter, in the simulation. So if hot Jupiter is formed in protoplanetary disks around the same distance where they are now, and this is what we expect these dynamics should be. So if you want to know whether the hot Jupiters will modulate the accretion onto the star and it's observable, whether it's observable, you could talk to Arturo. But here I will show another result. There are many interesting results from this particular simulation. So here you have a magnetospherical accretion, and then you have a circumplanetary disk around one hot Jupiter. So this hot Jupiter is at the magnetic truncation radii, where a lot of people suggest where the hot Jupiter should be parked to. And you can see that the disk of circumplanetary is actually in the vertical direction. It's not in the circumstellar disk direction. This may be strange, but after doing the simulation, realize this is actually quite natural. Because at the magnetospherical truncation radii, the material flows vertically. Right? So you have significant vertical flow, climb the magnetic field and to the hotspot. So if you have significant vertical flow, it's possible that you could form a disk just in the vertical, circumplanetary disk in the vertical direction, perpendicular to the circumstellar disk. Not always like that. Sometimes in simulation, we see the disk in the coplanar with the circumstellar disk. But in some cases, we could have these vertical disks. And in the simulation, there is another planet further out, somewhere here. So this may affect the planet's spin, hot Jupiter's spin. So towards the end, you see another planet further out. And this planet is further outside the magnetospherical truncation radii. That's why this disk is coplanar with the circumstellar disks. Yeah. So that's towards the end. From the theory, it seems that there is a very clear trend that the stellar spin has effect on magnetospherical accretion. For the faster rotators, like the truncation radii is larger than the co-rotation radii, you have higher outflow accretion ratio, stronger variability, more polar accretion. There are quasi-period signals. So all of these could be potentially observable. And in my simplest theorist mind, I feel like with the Ulysses have large sample, maybe it could test some of these theory trends. And there are also four sources with long-term monitoring. So with UV flux, you could get accretion rate. And maybe with the spectral polarimeter, you get magnetic field. And with these two, you could calculate the truncation radius relatively accurately. And then do long-term optical monitoring, you may get the spin of the star and get the co-rotation radii. So maybe there is a range of RT to RC ratio, and there may be some trend. So more robust predictions requires more simulations. We are trying to do more realistic simulations in the future. But that's what we have so far. Thank you.
Hey, thank you. Questions? All right.
Hi, very nice. I was wondering, you made a comment in passing that the infall velocity is around the infall velocity.
Yeah. Yeah.
Why is it not always the infall velocity? Why could it be higher than the infall velocity, the free fall velocity? I mean.
So it's a free fall from the magnetosphere truncation radii. So that's the velocity we measure at the surface, close to the surface of the star, where these filaments, that radial velocity is close to the free fall velocity you started from the magnetotruncation radii. So it depends on that radius where it is. That velocity could be different.
So for its local start velocity, for the radius where it starts its journey onto the star, that is the free fall velocity.
Yes. Yes.
It's just not always the same free fall.
No, it's not where it starts. It's like it starts its journey from here and then gets accelerated when they hit the star.
But it's still just gravitation. It's not no magnetic acceleration or so.
Yeah. Magnet didn't slow it down. That's in a force-free regime where material basically follow the magnetic field in free fall.
I mean, you could rearrange the magnetic field and but anyway.
Yeah.
All right, a question in the back.
So thanks a lot. Beautiful work. I love it. Fantastic. But I have a curiosity. How do you handle magnetic reconnection in this complex environment?
Yeah, so the manual reconnection is all numerical. So whenever the two magnetic field get into one numerical grid cell, we cannot resolve it, so it will reconnect. So the only thing we can verify this is the picture changes or not. It's just increasing higher and higher resolution.
Okay, but do you take into account the energy released at
No,
the magnetic reconnection?
No, so here we don't have energy equation involved. So that's what I mentioned. We want to do the radiation hydro so we could solve the energy equation. But that's very, very difficult. We are still not quite sure whether it's doable. That's because in this magnetosphere, in a force-free regime, so your magnetic energy is far larger than your thermal energy by order of magnitude. So if you have a code, you want to solve the thermal energy, which is a tiny, tiny fraction of magnetic energy. So you need to be very, very accurate. Otherwise, you will get negative temperature, and it's not realistic. So we are still trying to figure out what to do for the magnetosphere to do the thermodynamics properly.
Kat Barger, Texas Christian University. I was noticing that on the two videos that you showed, in both cases, there seemed to be texture by the poles of the stars, and I was wondering if that was included in your models or if those were just illustrations, and if they were included, like the equators also, it didn't look like the stars were oblique as well.
Oh, you mean oblate?
Yeah, oblate as well, and then there was textures on the pole.
Oh.
And so I was wondering, like, if you're including texture on the pole for, I assume,
like
associated with the magnetic.
Yeah, so this is the magnetospheric accretion that will have a lot around the pole. So you see this halo here. This halo is actually some density floor we have in the simulation. Because this region is very magnetic, so we cannot really simulate this very, very low density region. So there is some numerical artifact here. But this is like also rendering, like just to highlight some of these features.
Well, even on the very, very.
You mean the texture here?
Yeah.
Right? Oh, that is by the visualization. You have a grid.
I see.
You are trying to do spherical.
Okay, that makes more sense. I was wondering, like, how.
There's a question over here somewhere.
Oh,
okay. Any more? 1, 2, and then 3. All right, so I think James. Thanks.
Connor was first. It's a really interesting talk. I'm curious, for the planet that you have here that's forming with a vertical disk, would it end up having a vertical rotation axis as well when the formation process is finished? Or?
Yeah, I think it has a vertical rotation. We check the rotation, and it's a Keplerian rotation disk. So it has the vertical rotation. But not all the planets at this distance is doing this. Some planets is actually still have a coplanar one. Probably just flow in this region is very dynamic. Some are vertical motion, some are horizontal motion. It's very chaotic environment.
Very cool, as always. So you showed in some of the simulations you get quite limited accretion variability, but I guess that's averaged over the whole sphere. So if you projected it into a single observational view, would you get higher variability from different hotspots?
Yes, yes. So that is what we have for the periodogram. We have two periodogram, one considering the total m dot. This is total m dot, and this periodogram is just if you just pick one azimuthal angle. So this is more tracing the hotspot. Yeah, we have not really calculate the variability at different time scale. Like Carlos showed that at different time scale there seems to be some peak. The variability will saturate. So that's something we could do in future, just to track, just to make a more proper projection. Here, these are very simple calculations. Just pick one azimuthal angle.
Okay, and then Uma's will be the last question.
Yeah, I just had a question. In the beginning somewhere you said that you were going to compare this with the X-wind model. So are your outflows?
So with the X-wind model, overall, I think our model is more close to the Gaussian model. That is because the key part in the X-wind model is the magnetic field cannot penetrate through the conducting fluid, which is not the case in the simulation. The simulation you see is very, very turbulent.
Okay.
So you have very high turbulent resistivity. So the magnetic field is more like this, is penetrating through the disk.
Okay.
So you don't really have like an X point in the simulation.
Okay.
But you do have outflow, but these outflow are caused by the field inflation. But it's very highly dynamic field inflation. So it's kind of a mix of all the ideas people had before. But in a real simulation, you see that they happen at different layers.
Okay, thank you.
All right, let's thank Jawan again. All right, we're gonna, we need a second because we need to fix something for the online audience.
Okay, let's do it this way.
Program seems to be muted. People online can't hear us. Okay, thank you.
So, first of all,
Oh, we need a minute to see if we can fix this.
okay.
And then I'll introduce you. Did it work? Okay, so we're back on. All right, so it looks like things are working. So our next speaker is Ana Gomez de Castro, who will be telling us about characterizing outflows in T-Tauri stars with Ulysses.
Okay, so once again, thanks a lot to the Scientific Organizing Committee and our team working on splendid work and for the work you have done. So I'm going to talk about what we can do to characterize outflows. That's in these beautiful simulations I love, fast speaker simulations. But now we have to compare that with the real world, with the observation. So, for this purpose, I want to start my conversation for my talk. It's a nice view graph we prepared some time ago. And this is H down. And then you have down the range. Have it in X-rays is an X. Have X-ray emission, and that's and this is a galaxy image. Survey, ultraviolet survey, when you catch up the stars and the it's just a few seconds exposure, less than a minute. Going forward, I have a short history. The microwaves here. Is the red? Okay. Well, this is getting difficult. Okay, anyway. So I will start with a short historical view, and then I will go to the UV observations of the Taurias flows. We should think not only about the small scale, that's what Ulysses will do, but also on the larger scale. And then I will show the results of the analysis of what Ulysses is going to provide. So to begin with, I love this. I don't know, probably for many of you, it's not a known word, but I bet that for all of you, the Tauri stars are objects of Joy. But in this case, it's true, because Joy was the first person who compiled all these Tauri stars. And as you see, there are many Miss and Madam over there, included Henrietta Leavitt. So at the very beginning of the Tauri stars, there was a small female scientist contribution. At the beginning, when they were first discovered, it was thought that it was some sort of bizarre nova because it has rapid fluctuations in brightness. And but then, well, the people came to realize, our colleagues came to realize that they were in molecular clouds. They were thinking about star formation, and they thought, well, this is probably young stars. Then the first simulations started. These are early simulations where you can see the collapse of a rotating cloud and the molecular and the angular momentum of the molecular cloud driving to the formation of disk. And then everybody agreed that there should be disk. And now we know that there are plenty of disk, beautiful disk at all wavelengths. We have a Hubble contribution to disk, which is mainly on the left side. Okay, we have also ALMA, millimeter maps, and we also have the infrared polarimetry coming now with VLT sphere. And we have all this phenomenology, absorbing the cloud, producing the droplets, reflecting the stellar light, the debris disk. So we have a very clear, everybody had very clear that there should be disk, and disk has indeed been detected. But the big surprise came in the early 80s with the discovery of outflow, because nobody was expecting that accretion would result in outflow. And this, for probably the youngest of you, is very surprising because you are used to that. But for all of us, it was something really very, very striking at that time. And then what it was found is that the outflow happens perpendicular to the disk, and it seems to be accelerated by the disk. And then again, we have these beautiful, beautiful Hubble images of all kinds of outflows from irradiated jets, from class 0 sources, from binary systems that were able to give us a good hint of what was going on in many senses. And that complemented the views provided by molecular data. So let's talk about the UV observations of the Tauri outflows. And to talk about that, we have to start with an old telescope called the International Ultraviolet Explorer. And this whole mission observed for the first time the Tauri star in the ultraviolet, Herbig-Haro object in the ultraviolet. Okay, but that time, in the 60s, and Barsoomian has realized that these nebulosities detected by Herbig and Haro in Orion were really were associated with star formation, and shock waves were proposed for their excitation in the optical range. And then there was attempted a detection in the UV. So what was observed was the emission, the carbon-4 emission, which was extremely surprising. And in fact, when this first detection came up, everybody was very surprised, because that's one thing that happens typically to astronomers, to star formation astronomers, is that when you say that you want to do a star formation in the ultraviolet, everybody looks at you puzzled and say, a lot of extinction, how are you going to do that in the ultraviolet? Okay? So, well, they detected it, and it worked. And what they did is a splendid classification work, and they classified the herbivore objects in two main flavors or two main types. One were, one were the lowest citation objects, and the other were the highest citation objects. And later on, very high citation objects were discovered in the X-rays. So I put this table in there because this is something that you are seeing continuously, but here you have it at glance. Okay? There you have all the lines. So you have the molecular lines. There you have the highest citation lines that, like the carbon-4 we have been seeing today. But you have also single ionization lines, neutral lines, and you have also forbidden, not really forbidden, semi-forbidden lines. Okay? Which is the good thing about semi-forbidden lines, that they are optically thin. And as we will see in the complex environment that we have to understand, as it is the environment around the T-Tauris, well, you just have to remember the simulations. Being optically thin is useful. Okay? So the first thing that they detected is that the objects, the HH objects, were much more variable in the ultraviolet than in the optical. And they didn't understand that. So there was a monitoring campaign that was run in the 96 by Lissot and colleagues, and they found that this was caused by clumpiness, and that both components are together. Then the first models were successfully applied to reproduce the bow shock using optical and UV data. And then we have this small telescope that was built just over here, the Hopkins Ultraviolet Telescope. And with that, we obtained some fantastic data on herbivore objects that showed the level of clumpiness was so high that it was difficult to interpret with only one single model. The major contributions of Hubble to understanding jets came from the superb angular resolution, and here you have some examples like HH1, and also at the level of microjets, which you see here. It is funny because, well, this comes from 2004, and in 1993, we were obtaining very good results using the high-resolution camera in the Canada-France-Hawaii telescope. The other thing that has done Hubble for the understanding of jets from young stars is the study of rotation. And there is a group with Francesca Bacchiotti, Deirdre Coffey, Tom Ray, who have been working on that very hardly, and had done heroic efforts to detect this rotation. Why is important rotation? Because what we have been talking about, and we have heard about, is outflow. But if the outflows are magnetized, they are rotating. So detecting rotation in the outflow is also a signature of magnetization at these wings. So what are we trying to study with unresolved UV observations? Okay, what we want to study is this. Okay, so we have the star. We should not forget about the star. We have all this environment that we have seen, this internal magnetosphere. We have the accretion, the shock spots. We have the inner border of the disk. We have the disk winds that come in different flavors. And something I have just asked is the areas where the reconnection of the magnetic field drives to the formation of high excitation lines. So we have all this complex environment, and we want to understand it just taking a spectrum that goes from one certain direction and integrates everything along this direction. Okay, so that's our challenge. By the way, this that you can see here, this comes from real numerical simulations of the area where magnetic reconnection between the magnetic lines and the disk wind lines meet. Okay, so and this is a result that comes automatically, basically. But we are not talking only about that region, which is that here, but we are also talking about unresolved jets, because at the base of the jets, there will also be line emission, and we need to detect it to understand where this first refocusing is occurred. So when the realization that there should be this pinching at the base of the jet came to the community, several observation campaigns, analysis of the archives were run, and in this process, well, some lines were detected for that were, again, forbidden and semi-forbidden transitions, and the results that came were amazing, because we were seeing clearly in the semi-forbidden transitions stars like loop, where you could see the two components, the component that comes from the magnetosphere, and clearly the component that comes from the outflow. Or in white tower, you can see perfectly the outflow, and you can see in the forbidden lines. Everything was very beautiful until we took the data for RW Auriga, and then we got into this very complex structure that we didn't know how to interpret, and we interpreted it as an evidence that there was a sort of ring around the star that was producing this plasma, this emission. And then came the X-ray people, and the X-ray people detected X-rays from the jet, from the base of the jet. And then the paradigm changed, and there was some modeling, there were some models that were related with producing at the bottom of this magnetic structure, which is this wind, a magnetized this wind, producing a sudden ejection that would result in a compression and the production of X-ray radiation. And you have here an X-ray shock, and this X-ray radiation would also result in the photoionization cascade, producing emission that could be detected in carbon-4 lines, for instance. The point is that the emission in UV it was so weak that, well, it is difficult to detect. And more things to make the environment complex, and that we should keep in mind when thinking about the data, are related with the structure of the outflow. What we have seen today is something like that. The disk has a dynamo, it's producing magnetic field, and it's interacting with the star. When you do that, you have a magnetospheric flow, or you have a wind flow that is very poloidal. You see the arrows go basically perpendicular to the disk axis. However, when your field, where your disk is not, it has not a dynamo, the flow changes the direction, and the flow becomes very parallel to the disk. So dependent of not only the inclination, but also the magnetization of the disk and the properties of the disk, you can get different velocity components along the line of sight, what makes everything more complex. I am going to talk a lot about complexities. Okay? And these are the results from some much more modest simulations of what we have seen, but this is carbon-free emission. So this is the profile that we are seeing. Everything that you see there in yellow is emission that comes from reconnection. And as you can see, you have it's a very variable environment. And if we could see it in velocity, it would be also very variable. So everything is mixed up in your spectrograph, in your spectrum. So what is the result of that? What you get is like a broad line. What you get is the distribution function of all these measurements. And this is the tricky part, because distribution functions may look very much alike, representing things very different. So basically, everybody in here is working with a sort of toy model. I like to describe it as a Russian doll, because you have many shells that are superposing one to the other and nested, and you are having this wind flow. But you should think that in an MHD wind, you have 3 velocity components. And when you are very close to the base, you have a toroidal component that develops to a maximum and then decreases. So the wind rotates very fast, but only very close to the disk. Over there, the rotation becomes very slow. On the other hand, there is a component that is a radial expansion. And this radial expansion it starts more or less at the time where the pinching is important and then gets back. And then you have the theta component, the one that goes along the jet axis, that this goes smoothly. This shows in the profiles. Okay, so when you see these profiles, this corresponds to each one of these profiles that you see there correspond to a single ring. And what you find is that that is a single peak sort of Gaussian profile. This comes from the area that is dominated by rotation. And this one that comes as a two-peaked profile, this comes from this area that is dominated by radial expansion. And this one that comes single is against the jet, okay? That's the collimated area. So very careful with the simple interpretations of the profiles. More things. If you get into that and you put the kinematics and then you put into there the density and the volume, you end with, and the thermal broadening, you end with this kind of lines. And as you see, you may have two components, but they come from the same wind structure. They are not different structures. Okay, so careful also about that. So, and finally, one important thing that one should remember is that if you have a magnetized wind, the heating comes from the star, but also comes from ambipolar diffusion, which is this formula here. And there you have the electron density. So if you have a high electron density, the ambipolar diffusion goes down. And if you have a low electron density, the ambipolar diffusion goes up. As a result, what you get is your star ionizes the environment. It produces increases the electron density. So your ambipolar heating goes down. Then the radiation pushes it up, then goes down, and finally it acts as a heater. So you have always a very uniform temperature, which is around 10 to the 4 K, which is the temperature we observe all. Magnesium 2, carbon 2, silicon 2, all these single ionized species that we observe. Okay, you have it here. So let's go now to the data. This comes from different works. This is a work that was carried by a former PhD student of mine, Fatima. And what she was doing is to use these forbidden lines to study the magnetosphere of the stars. So we have to do a very careful work because what we have is many lines mixed. We call about carbon-2 forbidden transitions, but we have a mixed up silicon-2 and iron-2 forbidden transitions. Everything is in the same, all together. And to identify the density and the electron and the temperature of this plasma, you need to go to rather sophisticated least square fittings. And finally, from this study, we came up with a good measurement of the density and electron temperature regime. And as you see, there are some stars for which the emission is produced very close to the atmosphere, very high densities, and there are others that the emission comes from the magnetosphere, okay, lower density. And also, very few stars, only D Tower, Y Tower, and FU Ori had emission in these lines, had a jet emission in these lines. Okay, next one, magnesium 2. Magnesium 2 and Lyman alpha. You have here Lyman alpha from COS, and here you have the magnesium 2 profiles. Okay, these were 44 stars in the Hubble archive. And you go from these stars in here that are weak line Tauris with very simple profiles with the magnesium 2 emission and the absorption by the interstellar medium that in many cases it's optically seen because the intensity of these lines is twice of the intensity of the other. Both are of the same multiplet, but in other cases they are not. They are comparable intensities, so the emission is saturated. Okay? And what you also see is that in the Lyman alpha, this is in logarithmic scale, sometimes you only see this emission, that's the geocoronal emission in Lyman alpha. But sometimes you see these features in here, okay, and these broad wings that are related with the environment. The same matter that is producing the magnesium 2 is also producing Lyman alpha, okay? Then you can see that there are many, many different types of profiles, all a nightmare to interpret because either you go too simple, which is difficult, or you are overlooking important things. No? And so basically what we did is to you assume that the red part of the profile was not very much affected. We duplicated and measured 3 velocities. The velocity in the border, in the blue border, the velocity in the red border, and the velocity that we call the terminal velocity of the wind. And well, you can see that this, when we talk about the terminal velocity of the wind, we are not talking in the P Cygni context of the massive stars. We are talking about the component of the jet flow along the line of sight. So here you have a U loop, and you see that the star is seen basically pole on, and here you have this very prominent absorption, blue shifted absorption, very high terminal velocity. Here you have Ry tau, and for Ry tau you are looking basically along the disk, and then you have a much smaller component of the velocity, and then you have these measurements. So we did that, and doing that, we found out that basically there was a correlation between the terminal velocity and the broadening of the magnetospheric emission. We assume that this broad emission is magnetospheric emission, over which the absorption by the wind is overimposed. But also made a plot that still we are thinking about it, and is that we always found that the terminal velocity was larger than the escape velocity. And the escape velocity is from the star, and we're talking about this wind. we are still thinking a lot about this. We need to understand that, okay? And then let's go to Ulysses. So this I have prepared for you, and it's a summary of what is in Ulysses concerning this topic. So this that you have in here is what we had before Ulysses. So we have all these magnesium 2 and carbon 2 lines, and also we have some hot lines, helium, carbon 4, nitrogen 5, for much less stars that have been presented here. And this is what we have got with Ulysses. So we have like a 1.5 times what we had before. But we have only got it in this range, in the G130M, G160M ranges. What does it mean? That means that we have not access to magnesium 2 or carbon 2, neither carbon 3, neither silicon 3. We only have access to carbon 2 and to Lyman alpha, nothing else. And also, well, I have marked, because I know that this is going to be kept for you, I have also marked in red and orange those observations that are, in my opinion, very noisy and can be of a small use for the community. So basically, we have a double, basically double the number of sources we have available to analyze. And what has been done? Well, this was presented already the first day by Carlo Manara. And one is the study of the outflow using Lyman alpha, what I have just shown you. Well, it has been done in a systematic manner by Aralunantham and co-workers. And well, you have this very nice plot that shows that, well, some of the line is blue shifted in some cases, and in other cases is red shifted, and well, 40 stars more. Then we have the carbon 2 lines. These carbon 2 lines are in the range that has been observed by Ulysses. But as you see, comparing them with the magnesium 2, they are much more difficult to treat. But they have made an heroic work, and they have managed to determine the absorption by the fast wind and by this narrow absorption, which is close to the star. And they have this interpretation where you have a fast component that would be this fast absorption, where they measure the velocity at the edge of the profile against the terminal velocity of the jet projected on the line of sight. And they have this narrow component, which is narrow and is more or less centered on the line, that we don't know very well what it is. And it is subjected to various possible interpretations due to the difficulty of the context we are working in, and also due to the well, we need to know very well the wavelength the accuracy of the wavelength calibration. So this is it. Okay. So to conclude, what I would say that till now has been Ullyses' main contribution to the study of outflows from the point of view of measuring the outflows. I am not talking about knowing about the UV radiation and the impact of UV radiation in accelerating outflows, or in many other things that have been there during this meeting. What Ullyses is going to provide and has provided is a good set to study Lyman alpha symmetries produced by the outflow, and the profiles to study the carbon-2 multiplet, the UV1 multiplet. And well, maybe there is a very, very hot wind producing reconnections, events, or whatever, and maybe we can detect some signal in carbon-4. But this is basically it. Okay? And well, I just want to finish my talk leaving this for you, which is the program of future UV missions for any of you who might be interested on that to know. And this is it. Thanks a lot.
Thank you. We have time for a couple of questions.
Yeah, Ravi Sankrit, STSCI. So just curious, have you thought about then following up on these Ulysses sources with HST cost, the NUV channel, to get the semi-forbidden lines? I mean, are there any observing proposals for that?
No.
And if they are, would those be useful complement?
Of course they would be.
Okay.
So this is an invitation, because if it is an invitation, I will jump into it right away.
There's 10 days left for the proposal deadline.
Okay, great. I will do that. Thanks.
Any other questions?
Okay.
All right, let's thank Anna again.
Yeah, thank you.
Is it on? Or?
The green light has to be on, so you have to press it.
Okay.
All right, so our next speaker is Justin Campbell-White, who will be telling us about how Ulysses unveils links between protoplanets, disk substructures, and disk winds.
Great, thank you very much, Catherine. Yeah, so I'm a postdoc at the European Southern Observatory, working with Carla Manara and the Wonder Group. And I'd like to echo the thanks to Julia and everyone here for the tremendous effort on Ulysses and this workshop. And it's been really great to see all of the talks and what everyone's doing with these data. And yeah, thank you to Anna as well for showing an overview of some of the outer disk structures that we see, which, not surprisingly, we haven't seen that many of at this workshop. But I'm sure you're all aware that for low mass stars, it's pretty ubiquitous that we see these types of disk substructures in the outer disk. And in this work by Pint and collaborators, they were actually looking at the velocity channels of the sub-millimeter continuum images to try and reveal hidden companions that might be within these substructures, perhaps causing the rings or the gaps that we see. And as we've already seen from this conference, the only directly imaged protoplanets around the YSO so far have been around PDS 70. And whilst there have been lots of targeted observations to try and figure out if it is planets that are causing these outflows, we also know from theory that that various winds and photoevaporation, or MHD, can also cause these type of structures in the outer disk. And to try and probe these potential links, what we want to do is actually look at the inner disk of these stars and the accretion process and the outflows. I don't actually have the cartoon from Hartman et al., but I'm sure you can remember it, that all of that comes from the very inner disk close to the star, which you need spectroscopy to probe. And so the main question that I'm trying to answer here really is, if we're looking at these substructures and trying to pin down whether they're caused by planets or winds, the place where we really should start is PDS 70, where we know that the planets are causing the substructure. And so jumping straight into the Ulysses data on PDS 70, this was presented in 2022 by Skinner and Aldad. What you see here is the STIS observations. Unfortunately, there aren't COS observations. This was one of the archival targets that was added to Ulysses. But you can see across the ultraviolet wavelength coverage, a lot of the lines that we've seen so far in this workshop. And in this paper, they did a thorough analysis of these lines to present what was happening in the ultraviolet. So they were able to see that a lot of the emission that you see here is actually due to chromospheric lines that are higher up in the atmosphere of the star. And looking at the carbon-4 line, which is a known tracer of accretion, they were able to measure an accretion rate using the empirical derived calibrations. The Lyman alpha profile is actually a bit too low resolution with STIS, so they didn't actually do much analysis on that. And something new that they found from these UV data was the presence of these molecular hydrogen lines, which are quite small there. And if you remember from Nuria's talk yesterday, she said that this is not something that you'd typically see in a non-accreting star. And this also leads to the question, so is PDS 70 a weak line or non-accreting star, as it had previously been classified based on its H-alpha width and its colors? Because we do see evidence for accretion, so such as they showed here with the carbon-4 line, there's some weak indication of some continuum excess, which again is hard to disentangle from the lines, which are more likely due to chromospheric emission. And other works have also shown that that there might still be some accretion onto the star. And so this also leads to the question, if we have accretion, do we have an outflow? Do we have a disk wind, which we know are highly linked and correlated together? So this is where my work came in. We had some extra data on PDS 70 that we obtained from the X-shooter instrument at ESO. I show here the two epochs, so a very broad wavelength coverage. And these were actually observed in exactly the same way as the Penelope data, which was contemporaneous to the Ulysses targeted observations. So what we have there is absolutely flux calibrated spectra, which we can use to probe line fluxes, for example. We also, from the ESO archive, had a lot of observations from HARPS, which is a high-resolution spectrograph on a smaller telescope than the VLT. But nevertheless, you can probe the emission lines that you see at very high resolution. And one of the first things we wanted to just check with these data was this accretion rate measurement that, for example, Atom Thanatibode had done, checked with the magnetospheric accretion models, and we had that measurement from the carbon-4. We took the line profiles. I show here just an example of the higher resolution that we have from HARPS compared to the lower resolution of X-shooter. And we measured the accretion fluxes and found very good agreement with what had been shown in the literature. And for some of the lines, we were able to, using the higher resolution data, actually resolve each component, which is harder to do in the lower resolution. And for some of the lines, it required some accurate photosphere removal, which I'm going to come back to in a moment. So we clearly see that we do have some accretion onto the star. We think that this is happening. So coming back to the outflows in the wind tracing lines, as Uma showed this morning, one of the well-studied lines to trace outflows is the oxygen one around 300 angstroms. And I show here the composite of the HARP spectra. So all the different colors you see are all the individual observations. And then when you co-add them together, you drastically improve the signal-to-noise. You can see some indication of this line above the continuum about here. But what you can see is that these deep photospheric features make it quite hard to actually see if the line's really there, and virtually impossible to actually measure its properties. So looking at this in some more detail, we were able to carefully remove those photospheric features using a high-resolution template. And what I show here is the residual subtraction in blue. The input spectrum of those HARP spectra for PDS70 is in black. And the template that we used is in dashed orange. And once you apply this correction, you can then actually fit this emission line and measure its properties, so its kinematics. So we can see that it has a blue shifted peak velocity, which is commonly observed for this type of line, and it has quite a broad profile, which is also observed, but not so much with these types of stars, which are known to have large cavities in the dust and gas. So once we were able to get the properties here, this was the first detection of a forbidden line at this significance from PDS70, suggestive of a wind and an outflow from the inner disk. We then looked at comparing the properties that we measured from this line to other stars from the literature. So what I show here is the peak velocity of that line versus the full width half maximum. And PDS70 is shown as the star. The colored points, the circles are other transition disk stars, so stars with big cavities. And then the blue points are weakly accreting stars. And you see that PDS70 has a larger profile than other transition disks. And this suggests that the emission is actually coming from a very close region to the star. So in previous work by Banzatti and collaborators that Umar also showed us, they found a lot of correlations between these different properties of the emission lines and outer disk properties of the star. One of which was that as the cavity size increases, this line actually gets narrower as you assume that it comes from further out in the disk. And what we see here is that the line is clearly very broad, suggesting that its Keplerian rotation is coming from very close to the star. So it might be we have some combination of situations here where we have quite a significant inner disk still, which is producing this, what we believe is a magnetically driven wind originating very close to the star. Furthermore, when we look at the overall accretion luminosity of these stars compared to the line luminosity of that oxygen-1, we see that PDS70 is just above the distribution of stars here, where if you were to take this accretion luminosity that we measure for the star and then give this correlation, you would actually expect, sorry, the other way around, you would expect that the line should be sort of down here, so weaker than we actually measure it to be. So this suggests that not only have we detected this line, but it's actually quite a strong wind originating from the inner disk. And we can start to compare it to other systems and see, okay, if there are other that have similar properties to PDS70, so weakly accreting, also a big gap, like maybe this might help us to determine if there are planets there, if they have similar conditions. However, one of these other outliers that sticks out there is another very well-studied disk that is known to have a misaligned inner disk with respect to the outer disk, and there's lots of targeted studies to find the planets here, and as yet we just haven't found them. So the search continues, and as does the link between these outflows and the accretion properties of these stars and the substructures. So that leads us on to the data set that we now have, which at high resolution to study these forbidden lines, we have the Espresso and Juves observations, as well as all of the HST observations that are probing those molecular hydrogen traces, which I didn't talk too much about, but can also be associated with outflows. But what I'm mostly concerned with is these forbidden lines in the optical spectrum. So we also have a few more observations from Juves and Espresso. And you can see from even the forbidden line profile fits that the key step is really to deal with this photosphere removal and to do this for a large sample of stars. So a quick shout out for some previous work that I did that had the Ulysses and Penelope spectra in mind was this star melt Python package, which was developed to mostly measure the accretion tracing lines across a large sample of stars. So it really automates a lot of these processes, a lot of these steps to be able to extract the emission lines and fit them, and it's fully compatible with the Ulysses and Penelope data. And the work that I've been doing more recently is to try and incorporate the photosphere removal into star melt. So I show here an example of RY loop from Espresso, so very high resolution. This is one of the monitoring targets. And this is kind of the input we assume. So since we're here at Space Telescope, I'm not going to say anything about the tellurics other than we dealt with them. And what you see here is just the photospheric features of this star. So in black, that's the spectrum observed from RY loop. And this is the photosphere here. And you can see from this example, for example, there are two deep photospheric features actually in the oxygen 1 profile. And to be able to fit this line as commonly tackled, you can't really just mask through them, because by dealing with how you remove those photosphere, it might affect the shape of these lines. So the first step you need to do is find a suitable template of a close spectral type. And we've compiled a list of empirical templates at high resolution with tellurics removed. So for each spectral type, there will be a number of templates to pick from. And the first step is just to simply align these spectra together so that the photospheric features are lined up in radial velocity. And you have an initial guess of the broadening of these lines. The next step is to iterate over those broadenings and the veilings to get the actual shapes as close as possible. And we do this through a chi-squared minimization. And then that allows you to essentially subtract one from the other and remove these photospheric features. And then you can see actually in the profile that although there are some small residuals, you can then fit through the line and actually start to measure the kinematics. And so this is now an automated process that I show here some of the examples from different templates where when you run it through and you get your results, you can then see which one has the best residuals and the best fits based on what you can measure from outside the lines. And yeah, Carlo showed a preview of this yesterday, but what I'd like to note here is that all of these are for all Ulysses targets at high resolution, all very different spectral types and photospheric properties, and these are all completely automatic photosphere removals, where the blue line that you see is the photospheric subtracted spectra. So this is going to allow us to really go through all of the data we have and probe not only the outflow tracing lines, but also the accretion tracing lines. So I've shown only one example here, which is the most commonly observed oxygen 1 line, but you can do this for any of the emission lines, any region of the spectra, and get the results extremely quickly. So this is all going to be made completely open source as well once we publish it. So that's the work I'm currently doing. I'm happy to discuss it while I'm here and take questions.
Thank you. Questions?
Hey, sorry if I missed this, but did you attempt to fit the continuum excesses of PDS-70 to get an accretion rate that way?
Yeah, we did attempt that. So we used the fitter from the X-shooter data from Manar et al. And we were able to see some continuum excess, but when we looked at the goodness of that fit, which is done typically from the veiling of the lines, we saw an overestimate of the accretion rate that we measure. So this is actually ongoing work that we're doing together with Rick Klass, where we're trying to really probe the lower limits of what we can do with the UV excess. So this is one of the examples where we think that the accretion is above the chromospheric noise for PDS-70, but it's just right on that limit of what you can probe with the UV excess, and is actually an example where the line correlations are really useful. But they again require these empirically calibrated measures, which if we can tighten up those as well using the UV data, then it's a win-win, really.
Okay, thanks.
So to measure the wheeling, you assume that the accretion continuum has a relatively simple shape, and not many absorption rates in itself.
So there's not really any assumptions in terms of measurements. I think we're not aiming to provide veiling measurements, and the V sin I we provide is also effective versus the template. We're really just concerned with removing the photospheric lines as accurately as possible using the empirical templates, and to be able to then study the outflows and the activity tracing lines. So because there are already tools available that do the veiling measurements extremely well, we're not trying to replace that. We want the open source package to be able to quickly arrive at the activity spectrum. So yeah, this is very fast.
Thank you. Can you implement this software also for varying metallicities and varying H's as measured by the lithium-1 absorption, or is fixed?
So we're not implementing it in a sense to be able to measure that directly, although that's something that we're potentially going to look into, where you have a better handle of that through the synthetic spectra, for example, where you have your grid of metallicities or log Gs, and then you can see what the best fit is. That's something that we're actually discussing to work on with some spectra that Miel Vioque has from X-Shooter. But probably for earlier type stars, something that I noticed, and a reason why we picked the empirical templates, which are a combination of class 3 non-accreting stars and main sequence giant stars, are actually because the photospheric features for later spectral types match a lot better than they do with the synthetic spectra at this high resolution.
Any other questions? All right, let's thank Justin again. This is for the arrow thing, and this is to advance.
Okay.
All right, and then I'll give you a... All right, so our next speaker is Christian Schneider, who will be telling us about simultaneous X-ray observations of Ulysses CTTS monitoring targets.
Yeah, so finally we're at the X-ray regime, and as you all know, the X-rays are the origin of everything, and in particular for T-Tauri stars. So we have seen that sketch, I think, countless times already, but here is where that all the magic happens, and it's really here. In the original sketch, it's actually a question mark, but I do think that there's there are X-rays, and we can prove that. So this is the sketch of one accretion column that has been shown before, but the important part is here that you have the infall. And for the velocities and the characteristics of the Tauri star system, the infall velocities are 300-400 kilometers per second, approximately. And that produces a strong shock when the ramp pressure of the infalling material equals the pressure in the stellar atmosphere. And such a shock, or the post-shock material of that shock, is in the range of 1,000,000 Kelvin or so. And such a plasma emits X-rays, and predominantly X-rays, and it cools via the emission of X-ray. So all the accretion columns, the energy fluxes, the accretion rate measurements come from the energy released here in that accretion shock. And that is a spectrum of the accretion shock. You see that there's a lot of emission in the EUV there's also X-ray emission. And the important part is now that the X-rays are absorbed by gas, while most of the UV emission and the optical emission and so that would be just a pass through gas and would be absorbed mainly by dust. But X-rays are predominantly absorbed by gas. So what we observe or may observe is only that part here. And because X-rays are absorbed by gas, it's very important what the structure of the accretion funnel is. So in this most simple models, we have one single column that is homogeneous in density, and that would give you a prediction for what fraction of X-rays would escape from that accretion shock. Then we have pulsed accretion, where you have different individual blobs entering the stellar atmosphere and produce shocks. So we have what we have seen before is accretion columns with different densities, but individually homogeneous in density. Or what we have also seen here is one column, but with a density stratification that is dense in the core and thinner in the outside. And it's quite obvious that for the X-rays, it really matters which kind of accretion column we do have. And I think that all the simulations now point to more like a style of this accretion column. And that we actually do see X-rays from accretion is seen here, where we plot on the x-axis the X-ray luminosity and oxygen, because oxygen is one of the most prominent lines in the X-ray regime that we can observe. And then we plot oxygen 7 over oxygen 8, which is a temperature diagnostic for the X-ray emitting plasma that we do observe. And normal in quotes, active stars that are non-accreting are shown here in gray. And the downward trend is because the more X-ray active a star is, the hotter its corona is. Young accreting stars, however, are above that line. And oxygen 7 is actually the line that would be most dominantly produced by the plasma that you would assume comes from the accretion shock, so 1,000,000 Kelvin or so. So this excess of oxygen 7 here is indicative of an excess of plasma at the temperature that you would expect from the accretion shock. However, the luminosity itself is a little low compared to what you would expect from if it would be optically thin to oxygen 7 in the accretion shock. So this brings me to the program that we have made. So we wanted to use the opportunity that Ulysses presented us with the monitoring targets. So we wanted to see how the X-ray response is to perhaps changes in the accretion rate. And we did that with TW Hydra, with Chandra, with VP Tau and RU Loop, with XMM Newton. GM O'Reilly was unfortunately not granted for that program. And that is where it connects to the agreed methodology. So it's called HERA. So that is high energy radiation from accretion, and it's the origin of all that journey. So the first topic is the accretion shock properties. And this is the light curve, or the sequence of observations on the top. It's the sequence where we see in purple the HST observations, represented by the carbon-4 flux that has been measured during these epochs. And in blue is the X-ray light curve. And on top it's actually in real time. And you already see that the X-ray observations are much, much longer than the HST observations. This is seen here in the close-up, where we see that the HST observations are in orbit, and the X-ray observations are half a day. So they are much, much longer. And you see some variability in carbon-4 fluxes, but also in the X-ray. And when we go a little further, then we see that some of the most prominent variability in the X-rays here, for example, that is a flare, that's magnetic activity from the corona of the star. It has nothing to do with the accretion. And it's also here that there before, slightly before the X-ray flare, there's a flare in one of the near UV bands that we simultaneously observe with the optical monitor on board of XMM. And the top panel here is actually a little bit cheated, because obviously the count rates in the different filters are different. So I normalize them so they smoothly connect together. But that doesn't tell us more about the corona of the star, but not so much about the accretion. And the accretion is actually seen here. That's the oxygen 7 triplet. And oxygen 7, as I said, comes mostly, or may come from the plasma that accretion produces. And we see the recombination, intercombination, and forbidden line. And in normal coronae, we see that the forbidden line is actually 4 times stronger than the intercombination line. And the ratio between the intercombination and forbidden line, so these two lines here, that is actually density sensitive. And it turns out that the densities that one would derive from those line ratios is in the range of a few 10 to the 11. And incidentally, if we combine the first two observations that were obtained during the periods of phases of slightly higher accretion rates, then the density is a little lower, and then during the second part of the observations, when the accretion rate was a little lower. It's unfortunately not very significant, but that would make a lot of sense in this picture here when we indeed have this stratified accretion column with a dense core, and we do not see X-rays from the dense core because all that would be absorbed. We only see accretion from the low density outer parts. So if you increase the accretion rate, that thing increases in size, or the peak density increases. That depends on what you think, what produces availability. But in any case, the absorption towards the tau equals 1 region, so to say, for the X-rays would go further out, and we would see lower densities at phases of higher accretion rates. So the last thing that is something that I find quite interesting and also connects a bit to the magnetospheric thing is that when we have accretion, and this is a plot here, but there's one thing that is really missing in that plot, that is the corona of the star. And obviously, if we have 20% of the star covered with accretion columns, we cannot have a corona in that regions. So we can look if we see some changes in the coronal emission, then we have changes in the accretion rate. And then we look here at the light curves again, keeping in mind that what we see here, the top is, or in the bottom is mostly coronal emission, so magnetic activity, and then the top, it's a U-band emission that we think is mostly, or the variability is mostly by changes in the accretion rate. We see that the U-band fluxes increase while the X-ray fluxes decrease. The same is seen here. We see an increase in the near-UV fluxes, and the X-ray fluxes go down. And this is not only for BP tau here, but we have seen that already in T tau, one of the famous T tau stars, obviously, and the x-axis, again, the count rate in one of the near UV bands, and in the y-axis, the X-ray count rate, and they are anti-correlated. And in fact, it's not only seen in individual stars in the sequence in time, but also in samples of stars here, for example, for the Orion Nebula Cloud, where on the x-axis is really the accretion rate, and on the y-axis the X-ray luminosity. And again, higher accretion rates correspond to lower X-ray luminosities. And in fact, we already knew since a long time that non-accreting T tau stars, WTTS, are approximately twice as X-ray luminous as CTTS, which have accretion. So in summary, there are clear signatures of accretion in the X-ray regime. We see the excess of cool plasma at the right temperature of accretion. We see high densities that are lower than what you would need to produce the accretion rates. And we think that what we see is mostly the outer part of the accretion columns, very similar to other diagnostics, for example, in the near UV that Catherine has done. And then there appears to be a trend that higher accretion rates decrease coronal emission. Thank you.
Questions for Christian? I'll start over here because I never start over here.
Yeah. Okay, thank you. On the last point about the coronal emission being anti-correlated, is that primarily a consequence of a reduced volume of coronal emission, or that the emission is absorbed by something in the accretion flow itself?
I think it's more a volume. I don't think we see I mean, if we absorb, we would see differences in the mean photon energy, because only the higher energy photons would pass through the absorption material. And I don't think we see that. It's mostly a volume thing, probably.
Maybe I should have got up and gone. On this point as well, do you think now with the contemporaneous data we have the ability to answer the question that the reduction in X-ray emission due to the increase in accretion is sufficient to explain the quite large difference, factor 2 difference between the weak T-Tauri stars and the classical T-Tauri stars?
Well, the issue is a bit that X-ray emission in itself is, if it's the coronal part already is variable in itself. So you can have, if you look at Tauri star 2 days later, it could have a 2 times different X-ray luminosity just from coronal. We see that in M dwarfs, for example, in other active stars. We see variability in the X-ray flux or luminosity that can reach a factor of 2 within days without any changes in the accretion, obviously. So we would need quite long observations or large samples where we can conclusively say that because the magnetic activity is always there, that is stochastically changing the X-ray luminosity, as well as that the times when we have really accretion rate measurements from CALIS or from the UV modeling, those are relatively short times compared to the X-ray observations. So you would have to assume that really what we see in the optical monitor is really then a change that directly transfers to a change, one-to-one or whatever change in the accretion rate. It's more like, well, trend that we see, not that we can say it's really one-to-one between accretion rate changes and X-ray luminosity changes.
Hi. I have a curiosity. How often are you detecting iron K alpha in these stars?
Rarely, but that is, iron K alpha is seen not that often, and it's variable too. And I think there are maybe, you mean that is fluorescence of the disk. So you illuminate the disk with high energy photons and you see the iron K alpha fluorescence. And that is really relatively rarely seen in the X-ray regime. We do see that in T-Tauri stars, but maybe on a handful, 10, 20, so that I would know of.
Okay, any other questions? All right, let's thank Christian again. We can break for lunch.